It's much more correct.
The maximum disorder from this to this. Only shuffles can you do this turn up with this?
Well, the Marcus is staying put, despite how that
Yes. Mark is a symmetry center. You want me to sign anything like that?
I want the bell to ring.
You want a bell? I can imitate a bell.
Okay,
I
we go.
can bell you with my 5 fingers.
Okay. You introducing me?
Yeah, I'll introduce you. Then I'll introduce you.
Okay.
Okay, let's get started then. So our first speaker is Ilja Gerhardt, who is in the group of Gerhardt, right? So it's this rise of single solid state emitters in quantum optics.
Okay, thank you. So hello everyone. I hope you're still with good faith on the last day and motivated to hear something more. And I actually arrived yesterday and everything was very short notice and I prepared a talk. And yesterday, at first I thought maybe I should kind of change my talk and I should maybe tailor it more towards quantum information processing. But then a little later I thought maybe I just leave the talk as it is, because this is a pretty kind of rough and wide introduction to what we are actually doing. So there's quite a bit of right and left from single emitters, from quantum. So I start basically really to talk about single solid state emitters. So if we think about single emitters, the first thing which comes a little bit to our mind is also historically the first kind of single astrid atom, I would say, here in a kind of ion trap. But if you look in history a little bit further, you saw that also molecules were detected already in the 80s. So as a kind of single quantum emitter, a kind of nano-scale object emitting light. I was quite busy with these single molecules, and here and there I will kind of introduce some of the features of the molecules as well. So in the 90s, I would say there were quite some devices made. It's a kind of single photon turnstile device where you have a single quantum dot coupled into a kind of into a resonator or into a kind of photonic structure. I think this is from Peter Michler's publication here. And also at the end of the 90s there was a kind of new field being introduced by Gruber and co-workers, 97 science of single ND centers. And so this is one system I also will introduce quite a bit. So I mainly focus on these kind of two emitters here, and we have to realize if we kind of differentiate between these emitters, we have to realize these types of emitters are there in solid state. They are kind of embedded in the matrix, so it's not a vacuum system or something kind of complex we have to build here. It's really a kind of solid state. Eventually, kind of even in liquid phase, we can localize and find these single emitters. So if you think about single molecules, for example, which were kind of introduced in the 80s still, it's pretty nice because in principle you can really tailor such a single emitter. You can modify it chemically. So you can make a bound to some functionality in a cell, for example, and you can really kind of attach these single emitters. Maybe not this particular molecule, but you have kind of the way to kind of chemically modify these emitters. You can also fine-tune the spectral properties. So unlike an atom, which is kind of really has a kind of fixed transition, and there's nothing that can differ one atom from the other, it's kind of clear that you can really change this, that you have a molecule emitting in red or in blue or in whatever color you want. They can be made biologically compatible, so you can really kind of feed a cell and have a kind of water-soluble molecule, for example. And in fact, they are pretty easy to handle. So the single molecule business is a big business currently in microbiology. You can really find a lot of biologists just working with a single quantum emitter, in fact. So there's another emitter. Mainly, the entire sample is consisting of diamonds, and normally diamond consists of a pure carbon-carbon lattice. So you have this kind of four-fold kind of geometry here, and this is a unit cell where something is different, and you have a nitrogen instead of a carbon here, and then there's a vacancy on the other side. So if you look on the kind of spectral properties of this one, you can conveniently take such a simple laser pointer, excite the system from the ground state to the excited state. There's some relaxation normally going on, and then there's a relaxation from the electronic excited state down to the ground state, and then you have redshifted emission. So here it's pretty easy to just detect the redshifted photons. And this is the spectrum you would see. So I shine in exactly such a laser here at 530, 532, and then I get a big hum of redshifted photons. So these are red photons starting, let's say, at 570 up to 800 nanometers. So this is what you get efficiently out of such an emitter. So this is what I said basically. So you have a convenient excitation source. So such a laser is easy to handle and easy to get. You have an emission at 637, and you have a large hum, which is called the phonon wing, such that you can detect nicely also all these photons here. So of course there's not only a kind of single defect center of nitrogen vacancies in diamond, there are other defects which were kind of also researched in the last, let's say, 10-15 years. Also as single emitters, for example, the oxygen, again, the nitrogen vacancy here, the nickel vacancy. And I would say currently there's also a big kind of challenge to find more new kind of defect centers in diamond. For example, currently I think the silicon vacancy is very important, and the chromium vacancy is also kind of, which was kind of human-made in Australia. Very important is of course also here the kind of spectral properties. You see the nitrogen vacancy, which is which is the best researched vacancy in diamond, has a kind of broad spectrum here. The nickel vacancy has a very narrow spectrum, which is very nice. Yes, please.
Why is there a vacancy next to the defect atom? What is the reason why there's a carbon?
Let's say in principle there is carbon which is which has a kind of anti bond, so to say. So this is the way it forms. Let's say I have to admit that I cannot answer why there is such a structure, why it forms out like this. I come to the point of how nitrogen is forming kind of an NV center in diamond in a few slides, and then you will see that it's not always like this. But this is actually a defect which is pretty bright, so to say. This is what you see. So there are also kind of defect centers where you have only nitrogen, and then there's a kind of dark spin which you cannot detect, or which you actually can detect. But I think I'm coming to this point in a minute. So these are really kind of the defects which are kind of currently characterized in diamonds, and I think there's quite some research also coming up in the next years. So if you think about such an object, such a diamond has really big advantage, because if you have a molecule, for example, this is green fluorescent protein, which is really a kind of workhorse also in microbiology. There's something which is called single-step bleaching. So you make some research on it, you find it in a microscope, you see this kind of emitter emitting, and after a certain time there's a kind of decomposition event, the death event of the molecule, so to say. There's something changing chemically, and then it's off. If you think about nanocrystals, or how they are also often called quantum dots, I'm not too thrilled about this name for these kind of little fellows here. You also have the effect of blinking. So they kind of emit photons, they cycle from the ground state to the excited state, they cycle, and from a certain point on, they jump into a dark state. And then the kind of light is off, nothing is going on, and from a certain point they start cycling again. So you see this typical blinking in quantum dots. For NV center, it's pretty nice. So if you look on the timescale, so this is in seconds. So here, for example, with the GFP, you have a few seconds where you can perform research on these. With quantum dots, you have this kind of blinking behavior, also in the timescale of seconds, and this is in the timescale of hours. So there's just no way really to kill a NV minus center. And you can, let's say, yesterday in the evening I was talking a little bit about the NVs and how we get a really clean sample where we are sure that there's no contaminants on the surface. The early way was really to take the diamond, to put it into a 20-watt green laser beam and just to bleach everything else away. The diamond, the single nitrogen vacancy, just survives. So, and you can also really kind of make very, very tiny diamonds. That's also pretty nice. You can really have a few angstrom, or let's say a few nanometer object. Here the smallest fluorescent nano diamonds were kind of found to be 1.5 nanometer roughly in size. So this is about a 5-bit atom. So you can really also kind of scale this down. And this is pretty interesting for people doing biology again. So here you can have for example, cells. These are HeLa cells, fat with NV centers. And so this is a paper which was done in our group several years back, where you can really see the nanodiamonds in a kind of in a living cell nowadays. And important here, it's not a cytotoxic system, so you do not kill the cell, like for example with the quantum dot. So it's you can really have experiments in vivo. And if you look in this field quite a bit, there's also quite some development. For example, this is, yeah.
What's an HeLa cell?
Oh, I'm also not a biologist here, I have to admit this. I think this is, I would say this is roughly something like the guinea pig of the physicists to do biology. This is a little bit the approach. I think this is something which you can easily get. And you can,
So it's a type of cell?
It's a type of cell. I cannot really kind of give you any functionality or where it exactly comes from, but these are cells which are kind of existing in actual living organisms. And for example, last year, also in the group in Australia, there was an experiment. I think this is again HeLa cells. So this is the kind of artist picture of these fellows here, where they kind of fed such a cell with NV centers. And the interesting point is you have a nanoscale emitter, and you can localize it to a certain extent, so you know where the cell is. And with these kind of microwave antenna, I'm introducing this a little bit later. Again, you can also map the orientation of such a NV center. So you have a nanodiamond here, it maybe wobbles around. And this was one work last year, pretty thrilling, where they monitored an NV center in the cell for hours and hours and hours. So they were really doing the entire job here pretty well. So you could see basically over time the diffusion and the changes in the cell. So this is really microscopy. In principle, you have a kind of little thing, and there's no strong difference, for example, to a quantum dot or a molecule. So it's a nanoscale emitter. And so, but the NV center has much more. And of course, if you have just such a nano object, which you can localize, you also have, in this case, a kind of quantum object. So this is a very old paper, or let's say very old paper, 12 years now, where Christian Kutzifer was showing that if you have a diamond, if you have vacancies, these nitrogen vacancies, you can have a single photon source out of it. So you do not only have a kind of nanoscale object, you also have a kind of quantum emitter, which you can excite community with a laser, and then it emits only one photon and not two at a time. You also see here, if you kind of crank up power, there's something like a metastable state. So there's something where it just jumps in two every now and then. So normally you would expect for a G2 function that it just is one everywhere, and except there where you have your time equals 0, it's nothing. But in this case, there's metastable states, so you have such a behavior, such that there's a bunching behavior a little bit later after you saw the first click. So one big problem in general of diamond is that it has a very, very high refractive index. So it has a refractive index of 2.4 and you get up to count rates roughly up to 500,000 counts. This is the number of clicks you get on your detector. So you know the T1 time of your system, and you can roughly, or let's say the kind of effective T1 or the effective T1 time, which is the lifetime at room temperature. So you know roughly how many counts you would get, and this is only a tiny fraction. So you normally take a really fancy objective. So this is a lens for $5,000, and then you kind of extract 500,000 photons. In principle, there should be more, but we are unable to detect it because all the light is kind of trapped in this high index material. And the really crucial point is if we do really fundamental experiments in a cryostat. So here we are kind of limited by a factor of 10 again, because we have such a geometry, the lenses are not working as good as ambient conditions, and we have only 50,000 photons, which is not a lot per second. And again, then we have to realize, okay, if we look on coherent photons, which are coherently scattered, which are exactly coming from this transition at 637 nanometers, this is only 4%. So if you want to think about experiments like, for example, Honging-Mandel interference, where you need the kind of indistinguishably of two photons meeting on a beat splitter, you realize that you're limited basically to a few thousand photons per second. And that's pretty tough. So the question is how to get the light out there. So there are a number of approaches, and one approach is of course which was also pretty big in press by Marco Lanka here. They are these kind of nanowires where it's kind of a material, it's a nanowire made of diamond. The aspect ratio is excellent here. And somewhere here in the sample there is an MV center. So every now and then you find one, and then you have a strong directed emission to the forward direction, basically. And this also gives you some more counts. In general, there are a lot of people working on photonic structures, and then there's one system I would like to introduce you, is the solid immersion lens. I think this was also shown by Mr. What was her name exactly? Okay, yesterday, and this from the Hansen group basically. This is a structure how to efficiently extract the light out of such a system. So in principle, we have to realize we are doing microscopy on a single quantum emitter. So everything could be so nice if everything would be like on this sketch where we have a kind of infinite small point, and there's our NV center here down there, and then we could collect everything out of it. But unfortunately, this is not the case. We have something which is called the diffraction limit. So we know in the moment we kind of focus down, or even if we collect from here, we are kind of limited to a kind of airy disk of the diffraction limit basically. And this is a little bit given by the numerical aperture, which is kind of dominated by the angle of incidence here to our NV center, which is down here in the sample. And it's also kind of important that we have a refractive index here. So the index problem was kind of addressed very often, or is very often addressed with oil here, but you can even address it much better by taking just a simple structure made of diamond. So this is a kind of diamond half sphere, so to say, and this has a high refractive index, so we realize that the airy disk is effectively getting much, much smaller, so we are really having a much tinier focus. So this is kind of really, this is the outer lens here, so this is my aspheric lens. Then we have kind of a refractive index of 2.4 with this diamond lens, half sphere here, and then the total numerical aperture is 1.6. And this is really, there's only one objective on the market which can match up with this high numerical aperture. I've worked with these systems quite a bit in the last years, and they are really working pretty well. So we had some experiments actually with molecules, where we have such a structure with a molecule down here. And you see basically this is the overall experimental setup here. So in principle we focus the light through such a solid immersion lens onto the sample, so there's a little quantum emitter down here in the focus. And we have to realize that we collect about 10 to the 7 clicks per second. So you have to realize that yesterday I was also talking about such experiments. You really have an unbelievable collection efficiency here. So when they were recalling the G2 function of a single molecule, they had problems with the standard software from Becker and Hickel to start-stop with a mouse because everything, the whole buffer was just overrunning. So also we were able to efficiently kind of excite such a single emitter here, and we were kind of shining in 550 photons and introducing a pi pulse. So this was pretty interesting. So we were recording Rabi oscillations here. So there was a little flash, and it was kind of transferred to the excited state in a pi pulse with 550 photons. Also, an experiment what we were doing was kind of 50% extinction in the forward direction. So we were kind of handling in light here. There's a single quantum emitter, and then we had a kind of a detector in the forward direction here, and 15% of the light was swallowed, so to say, by the single quantum emitter. And of course, it's very important that the sample and the solid immersions are basically one thing, because the more far you go, it's not a focus which propagates in air or in some other medium. It really has to be close to the solid immersions in the evanescent field of the surface at least. So this also works in diamonds. So there was one unique diamond solid immersion lens made of diamond, entirely of diamond, from element 6. So we received this one day with FedEx, and it is a pretty tiny object. So you handle it with a tweezer, and I would say there were about 5 occasions where it was lost in the lab somewhere. So we were, oh my goodness, the solid immersion lens is gone, and just by cleaning it and just, for example, boiling it in acid, and we were able to show that we increased the number of counts here by a factor of 7. So let's say this is a single vacancy down here, just from the surface, and if we just flip it around by 180 degrees, we see much more light out of here. So this is also roughly the limit currently. I think Ronald Hansen groups, they are really performing very well. I think they have another factor of 2, so they have roughly 1 million photons per second. But there's still room for improvement to collect light efficiency.
Sorry.
Yes.
So in this case, the MV is in the seal.
Yes, correct. So this was it's a kind of a diamond slab which was kind of as a starter, and everything was grown on top of it. So it's a thin single crystalline diamond slab, and then it was overgrown with polycrystalline diamond. So this is basically what we do in our labs. So we try to find exactly a way, a little bit like the Hansen group, and also like the other guys, for example, in Ulm currently, to design such a structure, such a solid immersion lens in the focused ion beam. Basically, this is a picture from an electron microscope, and there we have a single NV in the center here, and then there's such an ion beam structure or a milled structure around there. It's always crucial because there's some residue here, and you really have to be very, very perfect to get rid of all the spherical aberrations. And one point which was interestingly complex, I have to realize, was to find actually the depth of the diamond, or the NV center in the diamond. So let's say the student started, and I just showed a kind of arbitrary image what the student was kind of, it's better now, but it's pretty nice to see that there are trivial problems which are keeping us busy every day. So here you see basically a kind of scan, where we scan, just make a Z scan. So to say we have a lens, there's a diamond, and then we scan it just in Z. So this is the Z direction here. So somehow you see that here are 2 point spread functions down here, so here and here. So I think you see them roughly, you see the surface, but you have to realize this is in micrometer here. So we have a surface here. We get a reflection of the surface which is micrometer wide. So where is now our surface? Where is our NV here? So there are really trivial optics problems we are addressing every day. So for example, for the surface we have a kind of angular Gauss-Hanke shift because we are coming in with a high angle. There's something being reflected not exactly in the angle of incidence, which is pretty crucial here. And of course for the point spread function down there, in the NV center, we have a lot of spherical aberrations. For example, this is just a perfect lens on the left-hand side, and then there's a slab of diamond, and you immediately have a kind of variety. It's not a kind of, even in ray tracing, not a tiny point where you can say, well, this is my focus. So here we have a lot of kind of spherical aberration, and we have to kind of fit or kind of make a super resolution also in Z, which is not super easy. So the NV has a lot of properties which are much nicer than what I have shown you so far. So basically I was only showing you the left-hand side here. So I was showing you, well, there's a ground state and there's an excited state. But the nice point is that there is there's a manifold of the ground state. So there's not only the spin 0, but also a plus minus 1 level. And the interesting point is now that we can play some games with this one, basically kind of shining in some radio frequency, or kind of not radio frequency, but mobile phone frequency here. So we can cycle this round and round. And the interesting point is, from this level, from the 0 level, we get fluorescence out of here. And from the plus minus 1 levels, it's pretty likely that the system goes to undergoes an intersystem crossing to the singlet metastable state, and then it goes back to the ground state. So this is a kind of optically spin readout of the system, and you immediately can do quite some things with this. So I think one of the kind of pioneer experiments, or one of the nice experiments, was really Fedor in 2004, showing that there's something like Rabi oscillations you can perform at ambient conditions. So you switch on your radio frequency field for a certain time, and then you look up in which state of the two you end up. And this is, in principle, just the light you have here on your APD here. So the crucial point here is what I wrote beside the graph of PRL, that you only have 30% contrast. So if I recall yesterday the near unity fidelities of readouts in your case and also on the IN case, this is just not competing anywhere. So the question is, where is all this population going, or what's going wrong here? And we have to realize that this is not only a single kind of system. For example, in this case it's a kind of negatively charged NV, but there's also something which is called an NV0 state. So then the negative charge is in the close proximity, as we know now, and this emits at 575 nanometers. So in principle, every now and then, this NV, which is kind of nice and good, has a transition over to the NV0 state, and then it's gone, so to say, and then we lost all the coherence, everything is forgotten, and then at a certain point we get back to the NV minus. So this has a lot of implications also for other experiments. For example, if we want to get the coherence phonons out of here. So here, this is kind of the overall spectrum. I was showing only a tiny picture in the beginning, but here you see 637, the NV minus, and 575, the NV0. So, for example, at ambient conditions, there's now, I think, Walter was one of the pioneers last year in PRL to show that you can actually detect in which state you are by shining in a red laser. So you take something like a 590 laser and shine it in. You wait for 200 milliseconds, and then you look how many counts you get, how many counts are scattered. And for example, here in this case, they have 2 NVs in an optical focus. So they can say, well, if we have something like 100 counts, these are 2 NV0s. If we have about 170 counts, it's NV minus and NV0. And for example, for this kind of coupled system here, if these are 2 NV minus, then we actually perform the quantum operation and then we do it. So they were really going towards higher efficiency and higher fidelity from this 30%. So for example, this is a virtual threshold here. So you say everything, if I have 200 milliseconds readout, if I'm on the left-hand side, I just don't do the experiment. And if I'm here on the other side, I just do the experiment. And that's the next step to get more light, to get more kind of coherence in the system. So when when we think about such experiments as Hong-Mandel interference, where we really want to have indistinguishable photons which are somehow correlated to the quantum state in the system, we have to cool it down. So this is the ambient spectrum here at 300 Kelvin, so something like now, how we feel. But if you cool down to liquid helium temperatures or even a little bit lower, you see that the zero phonon line is kind of coming out. And these are the photons we can use and then perform further experimental stuff with these. So this roughly goes to 15 Kelvin, so it's not necessarily needed to have it down to 1.8 Kelvin. So what we realized over and over when we were researching on samples and samples and samples, there are few samples where we have very low spectral diffusion, and there are many samples which actually look like this. So this is scanning over this line, so we have a laser at 637, so we scan it, and at a certain point you get light out of the phonon wing. So this is a frequency scan, so this is time. So we make a frequency scan, we have a line here. We make the next frequency scan, the line jumps. Next frequency scan, the line jumps again. So this is called spectral diffusion. Something is going on with the system, it wobbles around there, so this is really the nasty problems about kind of solid state qubits. I think all the ion people are really glad to have something which is really on resonance forever and a day. So but here we really have the problem that, for example, thinking about Hong-Mandel interference, getting two photons on a beam splitter to interfere, there's just no way with these hopping photons or hopping transitions. So we also realized that if we crank up the power, the spectral stability is just going down, and this is a quadratic process. So we had the feeling that this is a two-photon process. So here we see what we kind of think is the current picture here. So this is the kind of NV minus center. So we have valence band and a conduction band, and the two-photon process brings it up, pumps it up to the conduction band, and then there's a decay to NV0. And the nice thing is now that we could pump it back. So we can pump it with a 575 laser back to here, and then we are back in the NV minus state. So the negative charge is not very far away. And this is roughly the outcome at low temperatures. So I hope you can see it. Yeah, I think it's visible. So this is the earlier picture I was showing. And with repumping, so with an initialization pulse before each readout, we can repump it basically back to a more stable line. And I think there's room for improvement. So this is roughly a factor of 4, let's say in our terms of reduction of spectral diffusion. So this is one of the problems we were addressing.
Do you know why it gets worse with time? The graph on the right.
No. I have actually no clue. In principle, I would say this goes on and on and on. Let's say I think this is just an experimental occasion that we have it here going worse over time. It's not. Let's say we start at one point, and in principle it goes the entire way. So it's not like drifting away or something like this. It's not like changing very. Let's say I think we can go on and on and on.
So you don't think that would be repeatable?
Let's say there's a certain statistics involved, of course, because the system is kind of evolving, and I would not say that it's getting worse over time. I think it's in this experiment just getting worse over time. Let's say this is a subset of the data, and in principle the line continues. Also with a lot of wobbling, sure, but it's not like that. It's let's say this is half a second later, so that it's really creeping away, or it's not kind of catching up with such a situation. There's no start, so to say. It's not a kind of start experiment. We didn't start here and turn on the laser. It is just a section of all the experiments going. So the question is a little bit how can we scale up? So, and this is a little bit what we are doing and what we are trying to push. And now I'm coming also to the implementation here. For dipole-dipole coupling, you have to be very, very close you have to be closer than 30 nanometers to have an effective LiPo coupling. I'm doing some experiment with plasmonic structures where you have two NV centers or two molecules on a plasmonic structure. And in 2011 there were two groups, also the Hansen group was showing homomorphic interference, and also the Lukin group with two independent NV centers in different lines. And one important point I really like to mention is here that there's also the vision to kind of couple to an external spin. So you have a shallow implantation in diamond, so there's an NV center very at the surface, and then ideally you come with some object from the top and make a kind of coupling to an external spin. For example, to a free radical or to another NV center. So for this implantation, this is the normal way you have it. So you have a kind of focused ion beam of N plus here, and this goes into the diamond lattice and this scatters all around. So we do not know exactly where this goes. And the really crucial point is that we have a success rate of 1%. So we have to send 100 nitrogen atoms to get one single NV minus center, which is actually fluorescent. So there's a lot of dark spins which are around. So these are actually nitrogen atoms which are in there, which have a spin, which are not visible, which are not optically adjustable. And so, for example, also they increase the bar of spins around there and also lead to spectral diffusion. So all these implanted samples are not very good for cryogenic conditions and narrowband photons. So one approach to also to get this more confined, also towards coupled and entangled 2NV centers, is to take a mica mass. So this is it's a material which is out there in nature, and then there's a very thin channel through there, and then the implantation is made through this mica mass. And so it was pretty interesting. There was a student kind of building this up, and he was searching NV center pairs in such an area, in such an implanted diamond, and he was able to find about 100 coupled centers in such an implantation run. So very important, and this is a little bit the last point here, is the sensing. So in principle, we do not only have a kind of nice Q-trit here where we can play some games down here, but also with the magnetic field we can get these kind of degenerate levels to split. And in principle, if you change the magnetic field, this is what you see. So you have B equals 0, you have one transition here between these lines, and if you crank up the magnetic field, you see that the lines are just splitting linearly with a magnetic field. So for sensing, this is very nice. So this is exactly what I was kind of mentioning already. So you have a kind of NV center as a kind of sensor. You scan it, for example, with an AFM probe over a sample, where you have a sample spin, and you can really localize where is the spin here and what's exactly going on at which location. So you do something like nano MRI. One thing was performed by one of my co-workers, here some years back in 2008, where they had a little magnetic sphere here and there was an NV center in the diamond. So when they were scanning the NV center around there, there's one time the resonance condition fulfilled. And also I think there's a paper last year from the Lukin group, Greenolds and co-workers, where they were showing such an effect once more to really also highly localize, for example, a magnetic bead, and also to characterize the spins in such a system. Interestingly, you can also do it not with a single system. You can really scale up. You can take a lot of systems. For example, here you have a highly implanted diamond. So these are there are 200 NV centers in a square micron, and then you can kind of do this, basically image this on a CCD. So you know basically if you put, for example, a cell or something on there, what is the kind of a change in relaxation time, etc., etc. So I just show you a setup, the kind of an image from the setup, and then the artist picture of everything. So this is the setup how it looks. So it's really kind of a large slab of diamond. Then there's a flow cell around there. So and they're playing with gadolinium and living cells nowadays. So there is a paper coming out where they think about having a kind of diamond substrate to put some neuron on there and to image basically online what's going on in the neuron just by sending the spins which are kind of changing on the surface here. So you can also scale it up once more. So with a single nitrogen vacancy center, you have something like 10 nanotesla per square hertz. And if you take now a highly doped sample, something like a cesium vapor cell, a little bit in solid state, you can really scale it down to very, very high sensitivities. We are currently doing such a project, but it's pretty tough because we are just running into the problems of analyzing small signals on a large background, and this is the usual problem. And we are not limited by the NVs, but by our measurement electronics. So this is roughly what I was presenting regarding the NV centers. I was showing them as labeled and single photon sources here. No blinking, no bleaching, very nice. As a big problem is the light extraction here. Then the coherent manipulation, so the T2 time is in the order of a few hundred microseconds, very important here. And then also regarding the sensing capabilities. That's roughly it. So, and also let's say after I saw the little advertisement, what can be done and what is on the horizon, so to say, there's another system I'm working on, and especially the people in atom optics know these kind of blue residues of rubidium in vapor cells, for example, or in all the good atomic experimental setups. So I was researching last year quite a bit on rubidium in solid state matrices at cryogenic conditions. So for example in argon, krypton and xenon. So I was growing crystals in a cryostat and looking on the optical signal of them. So this is what we see as a kind of spectrum. Again, we can excite the system, for example, at 730 nanometer roughly, and then we see something like redshifted emission out of a bulk sample here of rubidium atoms and krypton. And I hope to scale this down to the single atom level, because rubidium is a very well understood system, and it would be very interesting to understand exactly the development also regarding a lot of atom optics experiments, if you could handle a rubidium atom in a solid state. So the big team is shown on the next slide. So this is the Stuttgart group. And I thank you, and I hope there are some questions and you're not sleeping.
Questions?
Oh, I'm scared.
No, I've got one. Can you, so T2 times the microseconds, can you imagine the way how that can be increased? So what will be the next things to increase it?
Let's say there are a lot of things there, and in principle you could imagine that that you scale up to 2 milliseconds or something like this. The more pure the sample is, the less spins you have in the environment. So normally there are kind of naturally found crystals which are much better than the implantations which we are currently having. So I think this is the way. This is material science to a large extent. So it's a little bit like your engineering work you were introducing yesterday, but this is the only way to get large.
I was interested in that fluctuation of the zero phonon line wavelength.
Yeah.
So did you investigate, for example, how dependent on the sample it is? Or
it's very dependent on the sample. This is really the crucial point. So if you think, or if you look a little bit in the literature, there are very good samples where you could see Rabi oscillations at cryogenic conditions and where everything is stable. But a lot of samples, and basically there was one sample where we could observe high spectral stability only. It's really crucial, but this is a kind of arbitrary natural stone which was shown here. So it was not the best sample we have, but but it's really tough. It's material science. It's
And then a rough estimate of the range of fish?
I would say 8 gigahertz. So this is the normal way. And then you have lifetime limited numbers of something like a few tens of megahertz.
This was done at low temperature?
Yes. There's no way to have such an efficiency of the zero phonon line emission at ambient conditions, because with phonons everything is kind of coupling with everything, and then you see, let's say, the difference in spectrum shows exactly that you have to have a kind of zero phonon transition.
So one theory about this spectral transmission wave is that you have these charges hopping around in the crystal, and if there's a charge nearby your NV, then that shifts the wavelength.
Yeah.
Can you correlate the quality of the sample with other impurities in the material?
In principle, let's say this is roughly what I said. You can, let's say, for example, if you have an implanted sample where you have a success rate of 1/100 to kind of actually get an NV center, NV minus center, then you know that you have a lot of nitrogen spins in there, which are coupling to your system, and of course we normally take a kind of natural stone which is as pure as possible, where we do not have any kind of spins nearby, which are kind of shaking everything.
Good. Thank you, Ilja, again.